I'm streaming. It's going live. Um. Oh. Hi
Is this
guys.
true? Are you actually streaming? Are you actually
Yes.
streaming after
Yeah.
15 years?
Yes. I'm gonna check
I
my.
see the notification. It's 80.
I'm gonna check my internet speed test. Oh, I still have 11. This is good. I can stream and hopefully you guys will get like poor connection, but it's better than no connection. Uh.
Uh-huh. Oh, wait,
Uh.
I need to find the freaking babe.
All right, guys.
Oh, you sent it.
Say hello to this to the the
I can't
Skibbity
find-
Rizzler. Oh, that is not what I'm looking for.
Why
There
do
we
you
go.
say...
Okay. I gotta finish my course.
Telling your viewers, unsubscribe right now.
Oh, my micro is going off. That sounds like my reheated DoorDash. I'm kidding. I'm gonna actually.
Say hello to DoorDash? What are you talking about?
What? Streaming in Ohio.
Say hello to DoorDash.
Okay, I'm gonna eat my food while I watch this. You guys are just gonna watch me do my Harvard stuff today. I have to do my coursework. I have to do all these.
Bro
and
is
then,
doing your coursework.
Yes, I have to do
Bro
all
is
these.
doing his coursework.
Yes.
Everyone should like a stream.
This is maximum productivity mode. I'm gonna go threest mode. Rah.
Yeah. You're
It's
just
so
gonna eat DoorDash right
over. I actually
You're
don't
gonna
have
eat, like, 10
DoorDash.
burgers and after.
I don't have DoorDash. I have lasagna. But yeah, I'm gonna do this today. So I'm just gonna sit here and skim through some of this while I eat my food, and then I'm gonna do my coursework, guys.
Of
and
course
then, and then, do I need to turn you down, Bluey? Burly Felix
No,
X Cyrus is
no,
not real, by the way. It's not a real ship. I made it up. Silex is not real. Burly Cyrus isn't real either. 10 seconds in and he's
Not
already
evil.
eating. Yeah, I'm gonna do this. I'm gonna watch this video while I eat, just to review. Then I'm gonna do my coursework,
Bro,
and
sorry,
then
you're
oh
not
my
making
God, let me
sense.
finish a sentence, Bluey.
No, I'm not letting you finish. I need everyone to know that you're unsubscribed.
Okay, Bluey's at like 40%. I don't know if you guys can still hear him, but yeah, let's check OBS. Yeah, it's pretty quiet. So, as I was saying, I'm gonna go get my food. I'm gonna come back. I'm gonna skim through this. Hi, Jeffin. Okay, if I could say, let me try to do this one more time without interruption, guys. Okay, so I'm gonna get my food. I'm gonna skim through this for a recap. I'm gonna do all my coursework. Then I'm gonna work on a project that I've been working on for a while, guys, and you get to watch me do that. Oh, all my to-do list post-it notes are falling. And then I'm going to oh, I forgot to do something very skibbity. I have to send an email first. Let me. Okay.
Yeah, guys,
Let me make
that's
sure I
good.
don't accidentally. I don't want to accidentally show all my. Okay, I gotta send something to somebody. I gotta send email. Browse this computer. Resume. Yeah, I'm trying to get a job, guys. I'm trying to get a job. Okay. I'll be right back, guys. I'm gonna go grab my grub real quick. Here, you guys can see again. And I'm gonna get a Mountain Dew, Bluey, just for you.
The beast is finally gone.
Bro is always talking about DoorDash.
What is that? What did you say?
I'm sorry, guys. I'm sorry.
Oh no! What did I come back to? Why is there a soundboard?
What do you mean? What do you mean soundboard?
Okay, I think I gotta hop out of this call, guys. I can't bear to be there any longer. I'm so sorry, chat. Let's see what you guys are saying. I haven't been reading chat. Wow. Not really anything. Okay, cool. I'm about to skibbity this toilet like it's tomorrow Sigma. Okay. Alright.
Okay, well, hello,
I'm gonna
Runoff.
fry my computer trying to do all this. Okay, so I'm streaming. I'm watching a thing.
CSFD's third section is 1.3. Mining is part of
Yeah,
the preceptor.
yeah.
An algorithm better than some other algorithms.
Algorithms, big O and omega notation, structures, recursion. Cool.
So, I hope to make a more sensible section, which is a powerful tool you can use to solve problems in computer science and a worthwhile tool to have.
Let's do some review, shall we?
So let's begin by jumping into our very first topic, which is how we can compare algorithms. In lecture, we had two algorithms related to really two types of algorithms. So one of them is how we use for searching, how we can find certain data from a data set.
This is
and the other
delicious.
for sorting, how we order data. Make things
Jeff,
more
and
efficient
don't
for
dislike my stream.
And we also talked briefly about these notations we can use to compare algorithms. I recall big O notation and big omega notations. We'll talk more about those in section today. Now, let's go back as a bit of a review and think first through some searching algorithms. So here, I have a list of people you can see on my screen. And currently, what do you notice? People here are not quite sorted by name. You have Matthew first, then Sonia, and Alyssa.
They're not sorted.
And I ask you all, what
It's not alphabetical.
in this case, an array of people, if we know the list isn't sorted? What kind of algorithm?
If we know the list isn't sorted, well, we could use selection sort. We could use bubble sort. We could use merge sort.
Then we use in this case.
I mean, the only real logical one here is like selection sort or bubble sort. We don't have to care too much about it, I guess. Like, it's just alphabetical.
So I'm seeing people say linear search, and linear search, to be clear, is
Oh, wait, I thought he was talking about sorting. Oops, yeah, linear
we
search.
start at maybe one side of this list and just look at the very first person, then the next person, then the next person, and so on. So let's pretend here we're trying to find this person, Alyssa, among these 7 people. So if we are a person, I could very clearly spot Alyssa. Like, Alyssa seems to be right here, right? That's not too hard for me. I can do that in one step. The computer has to look
I
at
got
only
ahead of
one piece
myself
of information at a
a little
time.
bit.
So it looks a bit more like this. You can imagine people being on a stage and us dimming the lights and allowing us to only see one person at a time. So if our computer might look first and see Matthew. And does Matthew Alyssa? No. So we're gonna look at the next person, right? So we'll turn our spotlight to the next person. We'll see Samya. And we're not quite there yet. We'll take the next person now. We'll see still Alyssa. So now we have Alyssa on our third try, going through person by person, left to right. This is an example then of linear search. So let's imagine that we go back and turn on all the lights, and we have people, in this case, rearranged. So notice how their names are in alphabetical order. We have Alyssa, then Cecilia, then Douglas, then Lucas. What kind of algorithm could we use now to search for Alyssa?
Now that it's sorted. Good question, guys. What algorithm do you think we should use to find you picked the wrong you picked the wrong industry. This is CS50. This is Harvard's free online no, Bluey, I've done this. I've done it more than enough review for this, but I just want to have something to watch while I'm eating before I start working today.
We saw this in lecture too. Some people say this idea of binary search. We actually saw binary search in our very first lecture when David took a phone book and opened it to the middle and asked if we went too far or not far enough, tore off half of it, and it kept going and going and going. So a similar idea applies to binary search, in this case with people too. So let's again dim the lights. Let's only look at one person. And if we're using binary search, we know it's perhaps most efficient to look in the middle and ask ourselves, have we gone too far or not far enough in our list? So let's look in the middle and think about Lucas. Have we gone too far in our list?
Hold on, Bluey. I got one for you. You hear that, Bluey? You know what that is?
Or not far enough. Seems like we've gone a little too far. If Alyssa's name begins with A, Lucas is after Alyssa in the alphabet. So let's say, okay, let's not worry about Lucas or the people after Lucas. Let's focus on the first half of people here and look in the middle of that. So it turns out the middle of our first half here is going to be Cecilia. And again, have we gone too far or not far enough?
Not far enough.
Seems we've gone a little bit too far still. So we do the same thing. We'll take that half of the problem, tear it away,
okay.
and now we'll focus just
I'm
on the very first
directionally
half. Turns out the very
challenged,
first person
guys. I'm
in that
sorry.
first half here is going to be Alyssa themselves. So we have two algorithms here, one called linear search and one called binary search, but it's also worth thinking about how we can compare
It's
them.
a
So let me ask
Mountain
you
Dew,
here,
Bluey.
how many steps did each algorithm take? If you can think
It's a
back.
Mountain Dew.
Just in terms of a plain old number of steps, how many did each take? Alyssa was the third person.
How many steps did each one take? Linear took 3, and binary also took 3.
In our linear.
But binary is binary is O log n, where linear search is O of n.
search, so it took
Binary search more
three
efficient
steps.
overall,
If you recall just now, our
guys.
binary search also took 3 steps. It started in the middle, divided in half once, and divided in half again for 3 steps. So it seems like linear search and binary search were the same here. They performed the same way. So I might then argue, well, it doesn't quite matter which one we use. I could use linear search or binary search, right? Each are equivalent. And what might you say, based on what you saw in lecture?
Well, the longer the list gets, the more time that linear search will take, because you have big O of n notation. So it's the upper bound of however many steps, or however many your number of elements in the array. So you have an upper bound of n, but you also have a lower bound, your omega, which would be omega of 1, because you could find it on the first step. But same with binary. Binary search, you could also find it omega 1, or your upper bound would be big O of log n. And that's more efficient because the more elements you have in an array, if we're not talking about 7 people, but we're talking about 700 people, binary search is going to be much more efficient because you can solve it in a fraction of the steps that a linear search would take if you had the same amount of elements.
If I were arguing with you that linear search is the exact same as binary search, what would you say? Some people say it depends on the problem size, which does make sense. Depends on the input that we get. So perhaps maybe we just got a little unlucky here, and both binary search and linear search took 3 steps. But it might not be the case in all inputs. And I like this idea of it depends on the size of our data set. So in this case, if we had a very, very big data set, we heard or saw in lecture, that binary search might be a little bit better for that big data set. So let's think instead as a computer scientist would, and think not just in terms of this one particular input, but in terms of input in general. In the general case, how well do each of these algorithms perform? So a better question to ask here is this one, which is, what's the greatest number of steps these algorithms will
I
ever
just answered this, guys. I just answered this. So, what's the greatest number of steps that this algorithm will ever take? So this is your big O. This is your upper bound. Linear search is O of n, because if you have n elements in your array, the maximum steps it could take, the upper bound, is going to be n steps. So if you have 100 elements in your array, the thing you're looking for could be at that very last position. It could be the 100th step. But binary search is only going to take O log of n, because it's logarithmic. You're dividing and conquering. You're dividing every time. You're just dividing the problem size down and down and down. So binary search, O log of n. Linear search, O of n.
And let's focus actually just here on our 7 people, right? Let's say, how long would linear search take, which is the greatest number of steps here? Seems like 7, right? So 7 steps. We have to go through all the people to find out
he means
how
in
many
this
numbers
example? Oh, shoot. I was wrong for both of them. Oh, okay. Wait. If he's talking about this problem specifically, linear search would take 7, and binary search would take, at maximum, 3.
4 or not. So it seems like 7. What about binary search, though? What's the greatest number of steps it would ever take if we had 7 people? I'm seeing n over 2, or like dividing it in half. And you're almost there. It, in fact, is a logarithm. So a logarithm allows us to take something and divide it in half again, and divide it in half again. So it's more appropriate here to say that linear search takes about 7 steps, and binary search...
What? It would take 3 here. I don't know what all this funny stuff is. I failed Algebra 1. This would be 3, guys. It would take 3 steps. Because you get your middle, and then you get your middle again, and your middle again, and then you're out of options, so it's 3
For
steps.
7 people, takes log base 2 of 7, which basically means however many times you can divide 7 by 2, which turns out to be something like, let's see, maybe like 3 or so steps.
Yeah.
So in the worst case, if you will,
That's what I'm saying.
linear search takes 7 steps. In the worst case, binary search takes far fewer, and therefore might be a better algorithm. So what questions do we have so far on this idea of comparing these algorithms using the worst possible case? Any questions?
No.
I'm seeing a question here about big O notation, which is where does that come in? So that's actually going to be our next step here. So we often don't think about problems in terms of the exact number of elements we're searching. We often might think about in an even more general case, like just some number of people, like n. If we had 7 or 8 or 10 or 1,000, like who cares? We just call it n, some number of people. And so now we could say, well, linear search, in the worst case, the greatest number of steps we'll ever take is going to be n steps, 1 for each person, where we assume we have n people, right? Now, binary search would do the same thing. It would say, let's actually not go through all n of them. Let's divide things in half and half and half again. So the most steps we ever take would be log
This
base
Mountain
2
Dew
of
voltage
n,
is
where
so
again, n
delicious,
the number we
guys.
have overall. It could be 10, 100, 1,000, and so on. But now, computer scientists, because we often work with data sets that are so large and so big, on the order of millions or billions of pieces of data, we don't often care about things as like robust as like, okay, is it log base 2 of n or log base 3? We care about even more general case. And that's where this idea of big O notation comes in. So we might say that linear search operates on the order of n steps. And in the same way, binary search operates on the order of log of n steps. So thinking here, not even about the general case of like, okay, is it 7 or 10 people, but just like, what are we actually doing here? How does the problem scale as we add new people? So big O notation then is used often for this question of what is the greatest number of steps?
I know exactly which teacher you're talking about, too. That's the one that got caught for being a you-know-what, right?
Per take. If you're more technical, you can think of it as the upper bound of the algorithm. The algorithm will never run slower than this. So questions then on the transition between talking in terms of individual steps and talking now in these general kind of hand-wavy cases. Question, is there a faster way than binary search? It's a good question. So if you get really into this, you can find other kinds of algorithms to search data, and there might be cases that could be a little faster than binary search. I don't know off the top of my head, but certainly there are researchers who are working on that kind of thing to figure out how we write a faster algorithm than, for instance, something like binary search. Okay, so let's keep going, and let's think about a different kind of scenario. So here we're talking about like the worst case, the greatest number of steps our algorithm will ever take, but there's some other case too. So let's consider this one, where we're still trying to find...
No, that's not me, Fox Dev. So the guy looks like he has an antenna. What are you talking about?
Okay.
His
So
hair?
Alyssa is the very first person we find for people. But we're still trying to find Alyssa, and we're using linear search. So let's say it just happens to be that Alyssa is the very first person we find. How many steps does that take? Well, just one, right? And now let's think too about a binary search. Let's say we have this input of people that kind of shuffle a little bit. We have Aaron, Amelia, Alex, Alyssa, Celia, Lucas, and Ramya, and we're doing binary search. We're still
One
looking for
step.
Alyssa. And if we were to do binary search on this data set, where would we first look? Well, the middle. So it took us only one step to find Alyssa here. So there's another question we could ask then, which is this. Well, first, how many steps does the algorithm take? Each one take? Well, we talk about how linear search took one instead of binary search. But in general, we could also ask this question: what's the fewest number of steps the algorithm could ever take? So with the O notation, we talked about what's the greatest number.
then.
But now we're asking what's the fewest number. the
Oh, wait,
algorithm could ever
omega
take.
then, my
And in this
bad.
case, we kind of simplify it and say what happens if we get lucky.
Wait. I'm gonna swear. Sorry guys. I'm way too into this food right now. I'm not listening. It's omega of 1.
Well, it turns out that in linear search, the best fewest number of steps we can take is just one, our first at the very front of our list. In binary search, it's similarly just one, our first at the middle of our list. So in this case, it's still the same. Linear search and binary search, the best case, they only take one step. Now, in general, as we talk about, computer scientists don't tend to think about one particular input. They think about general inputs, what happens in just the overall best case. And we could say, even if we had 10 people, 100 people, 1,000 people, the best case scenario, each of these algorithms would take one and only one steps. That's where this idea of omega notation comes in. So omega notation...
Good question, Michael. I'm simply this is Harvard CS50. This is their online computer science introductory course. Absolutely free. Really good introduction. I'm just doing this all the coursework and stuff to get more experience solving problems as a computer scientist, I guess. Because I can code on Roblox and everything, right? If I can code on Roblox, that's cool and all, but it's much more useful if I actually learn the whole ins and out of computer science. All the technical stuff that goes on under the hood and how to actually solve problems efficiently and effectively, rather than just coding Roblox like I have been. Sorry, excuse me. Coding the same stuff in Roblox that I have been doing for the last year. It's about furthering your knowledge. It's the pursuit of continuous learning.
says what, given any kind of input, would be the fewest number of steps we would ever take. And now here, too, is this idea that omega notation doesn't even quite care if it takes 2 or 3 or 10 steps in the best case. If it takes some fixed number of steps, it only is going to be written as omega of 1. And there are other things we'll consider too, which I'll show you in just a bit. But consider for now that even if it took a fixed number of steps, 10, 100, 1, all would be written as basically omega of 1, indicating it takes some certain number of fixed steps in the best possible case. So questions then on these algorithms. I see a question here, are linear search and binary search the only algorithms that we can search data with? Certainly not. There are many researchers who are working on other algorithms we can use to search data, and you might find some that are suited for a particular use case. And from lecture, you might have recalled David saying that there's often a trade-off between, let's say, between space and time. You could perhaps have a
Roblox programming is
be a
like
little bit faster in searching something.
brain-numbingly easy for the most part.
Question about, can we define an algorithm? So it's a good question here. Like, what even is an algorithm to begin with? We often say
They make it so easy to do literally anything.
Like in linear search, we look at the first person, the next person, the next person, until we get to the very end.
It's interesting.
Any others so far? Okay, so here's a question for you all then. Suppose that you are creating a new algorithm and you want to assess its runtime. That is, how quickly does it run? You find out that the
Yes, I
fewest
love
steps algorithm ever
runtimes.
take is 2 and only 2. And now the question is, what is the big omega notation for this algorithm? Keeping in mind what we just discussed. Suppose in the best case, this algorithm takes 2 steps. What would be the omega notation for this
Omega
algorithm?
2.
I'm seeing 2 answers here, which is actually what I had hoped for. So I'm seeing some saying it would be omega of 1, and some saying it would be omega of 2. So if we go back here, maybe we wouldn't have omega parentheses 1, but we instead have omega parentheses 2. And I think it's a good intuition. Like if you know that the best case will take you 2 steps, I mean, it kind of makes sense to write omega.
Let me read this. Fewest steps it'll ever take is only 2. Oh, it'd be omega of n then. Oh wait, no, that's not maximum. I'm stupid.
But it turns out that computer scientists, by convention, like to think of things as being on the order of some number of steps. And whether it takes 2, 3, 4, if it takes some fixed number of steps, we'll say it operates in omega of 1 to symbolize that it just takes some finite number of steps in the best case.
Oh, that's interesting. They actually didn't talk about that in the lecture. I'm trying to keep up with this. I probably shouldn't be playing it at times 2 speed. Kind of hard to ingest information, but that's actually good to know. On the order of omega 1 doesn't necessarily mean it just takes 1 step. It just takes 1 fixed number of steps. That's cool.
So not omega of 2, but instead omega of 1 by convention. So some other notations you might see as you go off and learn more about algorithms are these here. So on the furthest left-hand side, you'll see the big O notation, the worst case, if you will. So you'll have algorithms that, in the worst case, take some fixed number of steps. They'll be in big O of 1. There are other algorithms, like we just saw binary search, operate in big O of log n. They keep dividing problems in half and half and half again. There are still others that operate in big O of n. That means they have to take a look at every individual element that they're searching for. And then there are some that operate in big O of n squared, where for every element, they have to take that number of element steps before they can move on to the next one, and the next one, and the next one. And in general, we don't really care if it's big O of n squared plus another 10 steps at the end. In general, we care about the biggest term, n squared, n log n, or 1. And same thing for omega notation here, but now think about not the worst case, but the best case, or the fewest number of steps the algorithm could ever take. And the question here is, well, let's say the algorithm takes maybe 100 steps in the worst case. What would that be? Well, it kind of depends now. If the algorithm takes 100 steps in the worst case, we have to ask ourselves how many steps the
Cone? You
algorithm
said
took in
cone?
that case. But instead, how the
I'm not
steps scale.
cone.
So if the algorithm will always take 100 steps and only 100 steps in the worst case, that would actually be big O of 1, because it's some fixed number of steps. If, though, I were to add one more element, and you then need to do 101 steps, or if I added 2 elements, and you had to do 102 steps, that would be an example of an algorithm big O of n, because for every element I add, I have to do one more step. Questions 2 on these notations. A question about encountering algorithms in other languages, like Python, for instance, we'll see later on in CS50. So certainly, there's this idea that we can take most any algorithm and translate it into really any other language. So for the first few weeks of CS50, you'll be using C. Later on, you'll use Python. You can take most any of these algorithms and put them into any language you'd like. Good questions here. Okay, so let's try actually putting some of this into practice. And so the very first problem this week is one called sort, in which you're given some various sorting algorithms. So we've talked here about searching algorithms, but now let's transition to thinking about sorting algorithms. So in lecture, we saw 3 different sorting algorithms, and here they are, along with their big O and big omega notations. So notice here that we have merge sort, which we saw was among the fastest of our sorts. You can see that merge sort has a big O notation of big O of n times log n. And the same thing for its omega notation, big omega of n times log n. Now this is faster than selection sort and bubble sort. So we'll see selection sort here. It was big O of n squared, and bubble sort is also big O of n squared. Now the omega notation for selection sort, bubble sort is also omega of n squared, but for bubble sort, omega of n. So actually, I said earlier that merge sort is faster than these two, but can you think of a scenario where we actually want to use bubble sort as opposed to merge sort?
You would want to use bubble sort if everything in your array is already sorted, because omega of n, you'd only be I guess looping through your elements for the amount of time, or that's how many steps it would take. You'd loop through it once. It would take as many steps as there are elements in the thing. So you're not checking every single thing. Chances are, excuse me, chances are you have everything already sorted, and that is the fastest.
What scenario would we want to use bubble sort instead of merge sort? There is a case where bubble sort is faster.
Everything's already sorted.
It seems like it's faster if we are in one of our cases that seems like one of our best cases. And we're talking about sorting algorithms. Well, if we know our data is close to being sorted, and we just want to check, is it sorted or is it not? Bubble sort could be a way to do that, faster in this case than merge sort. And we know this looking at the notation here. We see omega of n for bubble sort, and omega of n.
Don't worry, this isn't like crazy math. Big O just means the maximum number of steps something takes. Omega means the fewest number of steps it takes. And n just means the number of things. So if you have an array of 10 things, this is computer science, by the way. If you have an array of 10 things, how many steps would it take to do each of these sorts? So for bubble sort, you don't have to know what this sort is right now, it doesn't matter. It would take, at maximum, n squared steps. So n times n steps to sort through an array of 10 things. Or n things, really. So this would be 10 times 10, which would be 100. So it'd have 100 steps at maximum to bubble sort an array of 10 size. But at fewest, it would only take 10 steps to sort that thing.
Time.
The log stuff is a little more confusing. It's logarithmic, which is basically just dividing in half.
Log.
I'll drop this course in chat if anyone wants to take it. It's completely free. You don't need an account or anything. There's coursework you can do. There's optional coursework. That's graded too, so that's what I'm going to be doing today after I get through this. I'm almost done eating. I probably won't sit through this whole lecture. I'll skim through the rest of it. But
for every step we do, we have to add in another
very,
log n
it's
steps
very
to merge sort.
cool.
But for bubble sort,
And
we
they
don't have to actually do
explain
that in this case.
all the ins and outs and all the basics and
a chart, and
all the
the sorting problem
fundamentals.
asks
I
you
love it.
to figure out the identities of 3 mystery sorts. So here you're given sort 1, sort 2, and sort 3, and your job is to time them and see which algorithm each sort might be using. And one approach here is to think about, like big O and big omega notation, the best and the worst cases. Give them those inputs and see how long it takes them to run, and then compare them. Compare those run times and see which one you think might best characterize the algorithm you are just testing. So here, our goal will be to fill in a chart that looks a bit like this, where we have a reversed 50,000 numbers. This is like the worst possible case. Our numbers are in the exact wrong order. We'll go through and time each of our algorithms and see perhaps which one runs the fastest, which ones run the slowest. And we'll do the same thing but now given a sorted list. Our numbers are in the best possible condition. They're already sorted for us, and we'll ask that same question, how long in general do each one seem to take? And so by timing our sorts, we'll be able to figure out, do they seem to run more equivalently to big O of n squared, or big O of n log n, or something in between. So in this case, let's go back to Visual Studio Code, and I will restart mine here. Once you connect to yours, you'll be able to actually download some of the distribution code for the sort problem, and you'll be given, in this case, 3 different sorting programs along with the inputs I just mentioned. So I'll wait for mine to start here. But our goal will be to look at each of those 3 sorting algorithms, time them, and make note of, let's say, which one might be most equivalent to the 3 algorithms we just discussed so far. So it seems my code space is ready to go here. Let me hide a few things to get out of your way. Let me show you where I have my files. So if you download them, you should be able to see them in your very own folder called sort. And I'll use this command called cd to change directory into sort. I'll hit enter, and now I see my prompt changes into sort. I can hit ls again, and now I'll see some various text files along with my 3 sorting programs, sort 1, sort 2, and sort 3. So now let me show you what's inside answers.txt. I'll say code answers.txt, and now I'll see what I'm supposed to do. I'm supposed to identify which algorithm each of these sorts uses. So sort 1, for instance, could use merge sort, or it could use, let's say, bubble sort. It could be any of these things. My goal is to type it in and figure out which algorithm this sort is using. And then down below, type in why I think that's the case. So let's try timing these, given the best and worst case inputs, and seeing how well each one does. So I'll go to my terminal here, and if you read through the problem specification, it'll tell you that you can time these sorts using this. You can say time, and then followed by the command to execute the sort. So in this case,
they start teaching you C because it's a very good language to learn the fundamentals. They do actually give you some tools. They have a library that makes it a lot easier to start off with. Like, you don't have to do car star for a string, or a car array for a string. They have a string keyword already implemented with their library. They have some other useful functions, like instead of scanf, they have their own functions for that kind of thing. Yeah. But yeah, it's actually not that bad, and they take you really slow. The coursework is a little crazy. If you've never programmed before, or just haven't had a lot of experience solving problems, the coursework does get pretty tricky, especially with like all the syntax for C and stuff. But if you just follow the lectures and take notes and stuff, you'll basically learn all the computer science fundamentals you really need to know. I did this last year. I didn't get through quite through every week of content, but I did get through most of them. But this time I'm doing the updated one, and I'm doing all the extra side content and getting as much practice so I can really ingrain it, yeah.
/sort1 and give it.
I'm just gonna see what he does with this example, then we'll get to working.
Scenario. Maybe I'll give it the worst case to begin with. I'll say, let's give sort1 a reversed list of 50,000 numbers, and just time it and see how well it does. So I'll hit enter. I'll see it's thinking. Maybe sorting this list for me. And now down below, I can see how long it took to take all 50,000 of these numbers and put them in order. So it seems like sort1 took about 4.64 seconds, and you're given 3 different times here: real, user, and system time. In general, you'll care about just the real time. How long did it take based on like a stopwatch in this case. So I can go back to my answers.txt, and I could say, well, I'll just make note. Sort1 takes 4.64 seconds in worst case.
I do think that is a good point, Paul. However, I do think C is the perfect language to start with. Actually, they don't start you straight out with C. What they actually do is they use Scratch first to really help you understand variables, functions, things of that nature, conditionals, stuff like that. Even the concepts of abstraction, which are really important for beginners to understand, because I didn't understand abstraction until much later into my programming journey. Like probably like a year into programming, I didn't really understand what abstraction was. I learned from a friend at the time who was telling me all this stuff when I was learning module scripts and stuff. But I didn't really understand like the whole purpose of reusing functions and passing things through parameters and all that. It was all very, very poorly coded. Even buy food to feed your cat, I didn't even know what abstraction was at that point when I was coding that game. It was bad. But they start you with Scratch so you can learn the fundamentals, and then they use C, and they have some of their keywords, like I said. They have their own library that you use. And they compare those things to Scratch, like all these different things that you learn, like formatting. They compare it to Scratch directly. And over time, you learn all the essentials, and you really go from not just understanding like the syntax, because that's obviously like the biggest hurdle, understanding syntax, but understanding the problem solving, which is the most important part, I feel like. Like understanding arrays and how to iterate through things, and all this different stuff and how to optimize code and have it designed efficiently and effectively. It's probably like one of the best computer science courses I could recommend to anybody. Better than any YouTube tutorial I've ever seen. Like, if you're trying to get into programming just to learn how to like make games or something, you don't want to care too much about what's really going on underneath the hood, then sure, go watch tutorials. But I think it's so crazy how I didn't understand, like I truly didn't understand data types until like watching this. Like I knew what data types were. I knew there was booleans, I knew there were integers, stuff like that. But with every high-level programming language, Python, Java, or not Java, Python, Lua, etc., stuff like that, you don't have to declare variable types. You don't have to specify like data types or anything. It all does it automatically for you. There's a lot of automation in modern programming languages, like high-level languages, that really abstract everything away, and you really don't get to learn those fundamental concepts unless you've taken something like CS50 before or a computer science class. That's why I struggled with Java a long time ago, because Java was a low-level language, and I was just trying to like learn it without any actual understanding of computer science. And the tutorial I was watching didn't really explain it nearly as good as Harvard did. But going from scratch, for example, which is what I made games when I was like 9 years old in, to Roblox Lua, it was a lot more clear there. But actually getting to understand the fundamental concepts, like the data types, memory, all that kind of stuff, arrays, all of that stuff really helps solidify your understanding. And now I'm doing, I'm coding stuff that I didn't think I was even capable of coding just because I watched a couple hours of this stuff, For example, if I go to some of my coursework, I'll show you some of the stuff that you do as part of the class, but also just demos I've done on my own time just to, just understand it more, and I don't know, it's really cool. I love it so much, and I couldn't recommend it enough. Definitely not the best like absolute beginner course, but I think it's like the best like beginner course for people that have touched a high level language, because a lot of high level language like people that people that use high level languages, like you really need to understand the low level language stuff to actually make stuff more efficient. Learning algorithms and stuff. I didn't know what an algorithm was. Like, I don't know what any of that stuff was. I don't know what big O or omega notation was. But, yeah. Like, you go from just making stuff like, like a simple program like this, just printing out whatever, right? And you can see they have string. They don't have char star or anything. They introduce that later on. Because they have their own library for training wheels, so to speak, and their own like get string function and stuff to take user input. But then you go all the way up to stuff like writing substitution ciphers. Like if I run this one, for example, and I give it a key, I'm just gonna do QWERTY. And I just type in some plain text. Hello world, this is my awesome program. It just ciphers it, and like it's pretty cool stuff. Like this is stuff I'd never be able to figure out if I never took this this class, It's like the fact alone that a string is just an array of characters back to back in memory. And a string literally isn't even technically an array of characters. A string is just a pointer to a character that then loops through those characters until it reaches a null bit or a null byte, which is like, I never even knew that. I didn't even know how memory worked when I was getting into programming. It's like, I wish I did, because there's a lot of cool stuff you can do with it. Like the whole ASCII conversion, how a character is literally just assigned an integer, so you can do math on characters. That's what this does, it just also I know my formatting isn't proper. This isn't technically how you're supposed to format in C, but that's just how I'm used to with Roblox. I'll fix this right now, guys. Oops. Yeah, you get the idea. But just being able to do math on like characters is cool enough as is. and just being to write really well-designed code. Like, this is the entirety of the main function. I have a function that checks all the arguments. God, another one of these. I wondered why they give me style points off. I thought surely that wasn't wrong, but you can just have a single line and then I just like having things on the same line, but whatever. You know, checking for things that are only letters, you know, repeated characters, like it's all really, really simple stuff, but actually just understanding the fundamentals really makes a difference. And you know, subtracting a letter, like this is like a cool concept just to think about. You're subtracting letters because they're just numbers. You can use them interchangeably, you know. And I don't know, it's pretty cool, stuff. And like yesterday, I just wrote this little Fibonacci program, which is a lot easier than I thought. Print out 10 digits of Fibonacci there. Print out 20 digits. Yeah, it's kind of cool. I have collapse as well. Say collapse 10. It would take 6 steps to get to 1 using the collapse conjecture, whatever it's called. I even made this before. I made this little... I don't know how well designed this was. I didn't really put too much thought into it. But I have this grid, and you can just specify an X and a Y, and it'll plot a point there. So, it's not the most efficient thing ever. It's not the most well designed, but it's cool. Oh, oops. Whatever. Yeah. I don't know, it's just cool making stuff and learning how stuff works underneath the hood. Anyways,
let's be more particular.
just continue going through this for a minute.
Like this. Now, I might also care about how the algorithm performs in the best case. So I'll go back to my terminal, and I'll then say, let's time it again, use /sort1, and now let's choose the sorted list, sorted 50,000.txt, and enter and see how well it does. Now that was a lot faster. That only took 0.3 seconds about. So I'll go back to my answers page, and I'll write that down. I'll say it takes 0.33 seconds to sort a sorted list already. And I keep going here, and if you're watching this not live, I encourage you to pause the video and go through and time the other sorts. If you are here live, we'll go through and time these ourselves and put them all together in our answer.txt. So let's keep going. I'll go ahead and say I will run /sort2 now. I want to time it. Time.sort2. Let me give it the sort.
I think I got the idea. Cool. Let's work on the coursework now. So I'm gonna start with just these two. Which one? Okay, this is the first one. A few algorithms for sorting a sequence. Yep, I know those. You'll analyze 3 compiled sorting programs to determine which algorithms they use. In a file called answers.txt in a folder called sort, record your answers along with an explanation for each program by filling in the blanks marked to do. Okay, I need to download that stuff. First, let me just make this, stuff. Let me go back to get my terminal back. Oh. Oops. Oh, wait. Okay. I think it was called sort, right? Is this called sort? Yeah, folder called sort. And wait, how do you make a text file? Oh, is it just? I guess it's literally just the extension. Okay, cool. Oh, that's not the one. Answers.txt sort. Yep. Learn assembly is their first programming language. That's awesome. By filling in the blanks marked to do. I'm assuming that's where I download them. Okay. Download distribution files. CD. Yeah. Get back to the main directory. Get. Cool. Code space. I can unzip these two, I guess. Whoa. Oh, whoa, that's a lot. Pascal. What do you mean remove sort? Does it? Oh, I see. It's just at the bottom there. Okay, cool. Multiple text files are provided to you. These contain n lines of values, either reversed, shuffled, or sorted. So, you just have... Wow, they were not kidding. Cool. I want to write a program that does that. It seems pretty easy. Wow. Yep. These different types of text files may help you determine which sort is which. Consider how each algorithm performs with an already sorted list. How about a reverse list or a shuffled list? It may help to work through a smaller list of each type and walk through each sorting. To run the sorts on the text files in the terminal, run / blah 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 and then the text thing. Make sure you sort directory. Okay. Oh, wait. What was it? Oh, I guess it already made it for me. I don't think I was supposed to make that. Oops. Sort 1 uses C++ code on a piece of paper. That's great. For starting off, it's not that bad just getting the concepts down and not worrying about syntax, but like once you're actually writing programs, like just writing it on paper is like so pointless. Once you get beyond like 7 lines, you know? Okay, so I guess that didn't show me the time. I probably should have read more. Oh, oh, run time and then dots. Okay. Was I not supposed to sort it? Is that unsorted now? Okay, no, good. It didn't modify the original one, I was about to say. I like that you can't actually see the, yeah! That's awesome. I like that you can see the actual, like, encrypted stuff. Yeah, that's smart that they don't give you the actual files to look at. That's cool. This one's a little structured a little differently than other problems. So I think all I have to do is just write bubble, merge, and selection, and just whichever one those go to. So I have to time them. So I have to time /sort1, and I'm gonna say random 5,000. So let's have a hypothesis here. So we're gonna run each one of these sorts on our random files first, because merge sort should be the most efficient at sorting all of these. So we'll look at whichever one is the fastest, and whichever one is the fastest on random is going to be merge sort. For bubble sort, the higher numbers will bubble up to the end. So, whichever one solves sorted the sorted ones the fastest. Yeah, whichever one solves the sortest ones the fastest should be bubble sort, and whichever one solves the reversed ones the fastest should be selection sort, because selection sort wait. I don't know. We're gonna test it. I know merge sort's gonna be the easiest, so we're just gonna do sort one. Oh, time sort. What? Oh, I didn't use the file extension. Oops. Okay. Whoa, that's fast. So take note of this. So sort one. How do we write our? How do you know? Okay. This is our time to beat. I'm just going to keep that there. Let's time sort 2 now on the same one. That one's faster. That one's a little bit faster. Okay, so that's our new time to beat. So, let's do our final sort, which is sort 3, and run that on the random 5000 again. That one's slower. So far, it looks like sort 2 might be merge, just because it has the fastest results here. But just to test this theory more, I'm going to time our random 500,000, or not 500,000, 50,000. Oh, sort 1. Hello? Oh, there we go. Okay. So, whichever one is the lowest here should definitely give us a definitive answer. Because the larger the sample size, the more we're going to see the difference in between the I don't know what I'm saying. Let's just time them again. Okay. Sort 2, random 50,000, text. That one's faster. So that one is, whoa, that one is significantly faster. That one doesn't even have any milliseconds. It's just thousands of it. It's like, actually no, wait, those are, I don't know, those are the decimals, and that's a 0. So last one should perform much slower. So sort 3, random 50,000. So sort 2 uses merge sort. When testing the sorts on the random files, sort 2 performs significantly faster than the other 2 sorts for a random set of numbers. Merge sort is the most efficient with an upper time complexity of O n log n. Cool. Okay, now I just need to test the other 2. All right. So guys, the last two sorts we need to check are bubble sort and selection sort. Insertion sort isn't one of the options, is it? No. Apparently, insertion sort is the fastest here. Merge sort is the okay, wait. Hold on. Hold on.
In this steps, in order to actually
So we're just gonna see whichever one is
complete. You sorted 5,000 numbers where those number lists provided what you'll list, and you might.
Oh god, my brain's fried already. Not sure how to solve. I'm not a cheater. Let's give everything a go first. So sort 1. Alright, you see it, Paul. So sort 2 should be merge sort. Because on the random numbers, it was the fastest. Let's try sort 2 on... Ooh, okay, wait. Here's how we can figure out which one is the... So if we go back to this table here, here's how we can figure out which one is bubble sort. So bubble sort has a lower bound of n, omega n, meaning that the lowest number of steps bubble sort can take is just the amount of steps there are or amount of elements there are in the array or the list or whatever. So if we test merge sort and bubble sort on if we test all these sorts on the sorted lists, bubble sort should be the fastest because you're going through every single element there is. Whereas merge sort should, in theory... Okay, well, actually, no, because merge sort is still going to be faster. So we're just going to compare the other two that we haven't done, which is selection sort and bubble sort. We're going to compare those on the sorted lists. Whichever one is faster of those two is going to be bubble sort. Because with a sorted list, your lower bound is going to be omega of n, meaning everything's already sorted, and that's the time complexity for it. So we're going to test sort 1 and sort 3, which are the ones we don't have answers to yet, and whichever one performs the sorting algorithm on the sorted list is the faster is bubble sort. So sort 1 on sorted 5,000 is that fast. Now, if we time sort 3 on sorted 5,000, it is slower. Okay, good. Now, what do you guys notice about this number? And what do you notice about the time complexity, the lower bound time complexity of selection sort, right? It's theta of n squared, meaning big O and omega for selection sort are the same. They're both n squared. It's going to take, at minimum, and at maximum n squared steps. So bubble sort, on the other hand, is only n for this lower bound, meaning that this third one must be bubble sort because it is faster than the other one. This other sort must be selection sort, and this one must be bubble sort. So we don't even have to do any of that other stuff. We can just say sort 3 uses bubble sort, and sort 1 uses selection sort. When testing testing sort 1 and sort 3 on the sorted text, the sorted files, sort 3 performed faster than sort 1. By this point, it is actually, hold on, let's just test just to see, because this third option, or sort 2, should be the fastest one in theory. So time sort 2 on the sorted 5000.txt. Yeah, that one's the fastest in total, but that's because merge sort is faster than anything in this situation. The fastest Thank you, Khan. Cool. I don't grind elite code, no. This is CS50, Harvard. Okay, so in theory, because selection sort and bubble sort have nearly or have identically the same upper bound minus a couple tiny discrepancies, we can both assume if we are running a selection sort on both a selection sort and a bubble sort, both on a reversed list of numbers, they should be the same speed in theory because they are doing the same thing. The list is reversed, so it's going from greatest to least instead of least to greatest. So in theory, selection and bubble sort should take the same amount of time. So if sort 1 takes the same time, roughly, as sort 3 on the reverse 10,000, which is what we're going to do now, sort 3 on the reversed 10,000, which is what we just did with sort 1. Oh, wait, that's actually faster. So sort 3 is... okay, I don't know. I'm gonna watch the video explaining it after, but logically this one is sort. Hold on, let's try it on a different one. Time. So when testing sort 1 compared to sort 3 on a sorted list, sort 1 performs slower, thus concluding it is selection sort, because selection sort has a has a complexity of theta, not cats versus water cone, theta n squared. What? Hold on. Let's watch this video.
Let's take a look at how you might have solved the sort problem.
Oh, my headphones turned off because I haven't had any audio in them.
In
for
this
a while.
problem, we gave you 3 different programs that used 3 different sorting algorithms: selection sort, bubble sort, and merge sort. But we didn't tell you which was which, and your job was to figure it out by timing these programs on various different inputs. For example, we gave you this file random10,000.txt with 10,000 numbers in random order to potentially sort. And one thing you might have tried is recognizing that both bubble sort and selection sort have a big O running time of big O of n squared, whereas merge sort has a big O running time of n log n. Then for large random inputs, you should probably expect that merge sort is going to be significantly faster than both bubble sort and selection sort. So if we try these 3 programs on a file like random10,000, but you might try it on some others too, you would expect that merge sort should be the fastest. Let's try it out. Let's time sort 1.
Okay, this one I know.
On random. It took the second it took for sort 1. Significantly faster than the nearly half a second it took for sort 1. But just sort in terms of how it also takes a little over half a second to be able to sort these 10,000 numbers. So based on that information, it seems pretty reasonable to conclude that sort 2, the one which was the fastest on dealing with these random inputs, is probably merge sort. Between the other two, whether it's selection sort or bubble sort, we really don't know for sure just yet, but it's probably a pretty good guess that sort 2 is going to be merge sort, and you could verify that for yourself by testing it on some other inputs as well. But now we need to figure out some way of distinguishing sort 1 from sort 3. Which one is bubble sort and which one is selection sort? And to do that, we can take advantage of what we know about each of their big omega running times. Bubble sort, we know, has a big omega of n running time. In an ideal case where all of the numbers are already sorted, bubble sort can sort the numbers very easily. It'll go through each of the numbers one pair at a time and realize that there are no swaps necessary, and then just declare that the numbers are already sorted in linear time without needing to make multiple passes through the array again and again. So we should expect that even though these two sorting algorithms had a very similar running time on a random file, if we gave them a big file that was already in sorted order, bubble sort should be much faster than selection sort. So let's try it out. The biggest file that's all in sorted order we have is sorted 50,000.txt with 50,000 numbers, each of which is in sorted order. And let's try timing sort 1 on that sorted 50,000.txt file and see how long it takes in order to sort all of those numbers and print them out as well. It looks like it took a little over 3 seconds for sort 1 to be able to sort and then print all of those numbers, recognizing that it's going to take some time to print 50,000 numbers to the terminal as well. But let's compare that then to sort 3 on that same input, sorted 50,000, and see how much time it takes for sort 3 to do the same thing, sort these 50,000 numbers that are already in sorted order themselves. Whereas sort 1 took about 3 seconds, it looks like this algorithm is taking closer to 7
Wait,
seconds,
are
more
mine,
than double.
did mine get backwards then? Hold on. Okay, let me try this again. So we need to do time sort 3 on sorted 50,000. 2.3 seconds. Oh, wait, it is faster. Okay, cool. So this one, sort 1 is bubble sort. Bubble sort has a faster running time. Okay, let's try it now. I think I just had them out of order because I didn't test them properly, but... Cool. Yeah. It's good. Got some things off my to-do list. Just gotta submit this now. All right. Cool. There is. Oh. Okay, this one looks easy. Distribution code. Okay, cool. Let's get some music on for you guys, by the way. I know I haven't been very accommodating. Wait, I already have a tab open. Or actually... I got reading ambience. Okay, cool. So oh shoot. Oops. There we go. Oh, this time they give us some boilerplate to work with. Cool. Whenever you extend the functionality of existing code, it's best to be sure you first understand it in its present state. Look first at the top of the file. The line hashtag define max9 is some syntax used here to mean that max is a constant equal to 9 that can be used throughout the program. Here it represents the maximum number of candidates an election can have. Notice that plurality.c then uses this constant to define a global array, that is, an array that any function can access. But what, in this case, is a candidate? In plurality.c, a candidate is a struct. Each candidate has two fields, a string called name, representing the candidate's name, and an int called votes, representing the number of votes the candidate, that's a fun word, candidate has, candidate. Listen to me say candidate for freaking 20 minutes now. That's simple enough. Now take a look at the main function itself. See if you can find where the program sets a global variable candidate count representing the number of candidates in the election. Number of candidates. Int candidate count. What about where it copies command line arguments into the array candidates? Yep, candidate count equals the arg count minus 1. Right, because you're getting rid of the program thing. If candidate count is greater than the max amount of candidates, print that the maximum number of candidates is max. Return 2. And then loop through the candidate count, or loop through for the amount of candidates rather, and make the ith candidate, make their name equal to the second position in the argv plus I. So I plus, okay. So it's I plus the next one, because you have to get the one to the right, because the first argument in your command line is going to be the name of the program that you're running. So after that, you just set the vote amount equal to 0, because you just need to set that to 0 by default. What's up, Goosenford? How's it going? Peter, the horse is here. And we're asked to type in the number of voters. Int voter count equals get int number of voters. That's simple enough. Then the program lets every voter type in a vote, calling the vote function on each candidate voted for. Finally, main makes a call to the print winner function to print out the winner or winners of the election. We'll leave it to you to identify the code that implements this functionality. If you look further down in the file, though, you'll notice that the vote and print winner functions have been left blank. This is all we have to do. They just want us to fill in these two functions. That's new. I kind of wanted to write all this, low-key. Whatever, they did it for us. It's fair enough. This part is up to you to complete. You should not modify anything else in plurality.c other than the implementations of the vote and print winner functions and the inclusion of additional header files if you'd like. Damn, they don't let me do this on my own? Ugh, but I wanted to write everything from scratch because it's... Oh, man. I'm not that bummed about it. I just like solving problems, you know? But I guess we still have the most juicy problems to solve, which is actually voting for the things. And this is just practice to... this is an excuse to practice structs as well. First, though, I'm going to be right back in 2 seconds. Okay, guys. You guys want me to take a detour for a second? Actually, no. We're gonna lock in and finish this. We're gonna lock in. Peter, the horse is here. Alright. So. If not equal. Oh. If not equal to vote. Wait, let me see the demo again. Okay. Oh no! Oh no, he's here! Oh no! Oh no, I gotta end the stream. No, I'm kidding. Okay. So. Okay, so we're just gonna check if vote. Okay, so name. Oh, that's light work. Are they for real? All we gotta do. So listen, here's what we do. So all we needed to do, all we need to do for this function, we're just checking if it's not valid. So if it doesn't return true, so if it returns false, then it's going to print invalid vote. Otherwise, it's just going to continue because it doesn't matter. But all we need to do is have a case. So check to find if candidate exists, and if true, return true, I guess. So how are we going to do that? How are we going to find the candidates? So notice here, we already have an array of candidates with our struct candidate type. In theory, and I don't think this matters if it's linear, it really doesn't matter if we do a linear search here, because this is just going to be such a small list. The maximum it can be is 9 elements. It doesn't matter if we have a linear search. We're not trying to do an entire binary search. We don't need a binary search. I mean, we could, but we don't have to, just because the time complexity really does not matter that much. You're only going through a few elements anyways. So we're just going to do a linear search, and we're checking to find if the candidate exists. If true, then we're going to return true out of the loop. So all we're going to do for int I equals 0, I is less than wait, how do we get the length of an array? Hold on, I forgot about that. Size of. You're so true. See, this is a problem that I could solve very easily in Roblox because you can just loop through the table itself. But in C, we have to find more elegant solutions to the same problem because we don't have the conveniences of high-level programming languages. Instead, we have to find some other functions. I guess size of would allow us to do this. So size of is just going to get us, I guess, an int. Yep, an int of the length of the array divided by the first index. Okay. Okay, returns the size of the array in bytes. That's what we want. Of a single element in the array in bytes. So yeah, I guess we don't even. Oh, they have generative AI. Okay, so returns the total size of the array in bytes, and then it returns the size of a single element in bytes. Oh, okay. So this is good because this is another example of where knowing the underlying low-level concepts really help us. Because think about it. If what we're doing here, let's say we have an array, right? And an integer is not a single byte. An integer is going to be 4 bytes, for example. That would mean the total size of our array in bytes would be 20 because we have 5 things in our table. Each one is 4 bytes because they're integers. So what you do is you take one of those elements, and remember in C, arrays can only be one data type. You can't mishmash them like you can in modern high-level languages. So you take the size of one and divide it by the size of the total to get your remainder, which is exactly what we are looking for. So all we need to do here is we just need to get the size of the array. So we're going to say int length equals size of candidates divided by the size of candidates 0, the the 0th position of the candidates table. So for I to length, I'm just going to increment I. If stir compare, so we need our string okay, we do have our string library. If stir compare name candidates I, return true. That's all we need to do. That's our entire implementation for our that's our vote thing. That's all we need to do for it. Then for our print our winner, oh wait, we need to actually increment the vote as well. Okay, that's exactly what we had to do for the print winner. So, okay. What we need to do is initialize highest vote count. Oh, wait. 3 star stream. I like how they're even saying that we don't need a sorting algorithm for this. And sorting can be expensive. So all we need to do, so the maximum amount of votes actually, so the max votes possible for a single candidate is equal to the maximum oh wait, no, we need the voter count. What the freak did you say, Turt? Wait. Hold on. I'm overthinking this. Oh, brother. This guy's lying. This guy's a fibber. He's a little liar. So let's think about it. How do we find the maximum number of votes in this situation? Because everyone, in theory, the maximum amount of votes could just be the maximum, or just be the number of, the maximum number of votes is just how many votes that candidate, or how many voters there are. And we can't touch the, this code at all. I guess that's part of the problem, because if we could simply pass in the voter count here. Okay. Here's what we're gonna do. Total votes. Let's get the length again. I don't like having to repeat that, but they don't let us touch anywhere else. Print I equals 0. I is less than length. Increment I. We're going to increment total votes by the candidate's I dot votes count. So we're going to add the number of votes a candidate has to the total amount of votes, and then we're going to compare to see if which candidate has the highest amount, I guess.
And asking will it, and the print, because remember, vote function would return true. Of course, if we had voted for someone who wasn't in this election at all, for example, Dave, we wouldn't update any vote totals, and our function would return false. So that's the vote function. The second function you're going to implement in this program is print winner. And the print winner function is going to be tasked with printing out the winner of the election. So in this function, you're going to print out the name of the candidate or candidates who have the most votes. Because remember, it's possible that at the end of the election, multiple people are tied for the most number of votes, in which case each of them should be declared a winner, and you'll want to print out each of their names. So in this case, where Alice has 3 votes, Bob has 1 vote, and Charlie has 2 votes, Alice has the most votes, and Alice is going to be declared the winner of the election, so you should print out Alice's name. But consider, for example, these vote totals, where both Alice and Bob each are tied for winning the election at 3 votes each, so your program should print out Alice on one line, and then Bob on the next line. After you've implemented these 2 functions...
Oh god, how am I going to do this? How can I design an elegant solution for this, do you think? So let me reconsider this. Wait. 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 I don't know. I'm gonna cheat. Time to cheat, guys. Actually, well, we're not cheating. Don't worry about this. Don't worry about this. This is academic honesty. I'm not cheating, guys. I'm not cheating. Academic honesty. Okay, cool. Okay, so let's see the max votes. Well, first it's gonna be 0, right? Actually, they already have a thing here. Why'd I even... I don't even need to do this. They already have a candidate count. I didn't think that through. Okay. So instead what we're gonna do, we'll check if, okay, so the votes of the current candidate is greater than the max votes. Right? Because we're checking if the current candidate has more votes than the current max. So this way we'll loop through and, okay, then we'll set max votes equal to the vote count. Okay, so that way it'll go through every single one and find what the max vote amount is. And we just need another loop for this. They said not to worry about sorting them or any of that because that's just more than we really have to do. That's kind of overkill. So same loop here. I don't like having to repeat the loops, but I guess they do serve their different purpose. Oh, and then, okay. And then all we do is we just gotta check if the current candidate vote count is equal to our max vote count. And then if so, we're just going to print f %s \n and candidates I dot name. And this should work. Let's cd plurality dot slash plurality. Oh wait, make plurality dot oh oops, candidates I dot name. Make plurality dot slash plurality John, Joe, Gabe. 10 voters. What? John, Joe, Gabe, John, Joe. Oh, shoot. Oh. Um. Okay, this will work. Cool. I think this works.
Cone, you are not as skibbity sigma as you think you are, okay?
This is VS Code online. This is an online version. Okay, cool. Let's see now. This should work. Let's submit. Cool. Style it now. I think my style's good. Looks good. Submit. And then we only have one more to do. Yep. Submit that. Cool. Now we have two different options here. Runoff. Oh. What the freak is... Oh my god! I'm not doing all that! I'm not doing all that. That's it. That's it, Ducky. Let me just see the demo for this. I'd rather watch the video, actually.
Let's dive.
17 minutes? How long is this one?
Let's
Also 17 minutes.
now dive into Runoff.
We're gonna watch
In Runoff,
these.
we're going to take advantage of ranked preference voting. Whereas in Plurality, each voter only got to vote for one candidate. In Runoff, a voter might be able to rank all of their candidates in sequence. So the ballot might look a little something like this, where they have a space to fill in their first preference, second preference, and third preference, for example. One voter, for instance, might want Alice as their first preference vote. But if Alice can't win, their next choice would be Charlie, and if Charlie can't win, their next choice would be Bob. So this is what a ranked preference ballot might look like. How then does the runoff vote actually work? Well, the runoff vote is first going to say that every voter should rank all of their preferences, first, second, third, up to as many candidates as there are in the election. If any candidate has a majority of the vote, meaning more than half of the votes, then that candidate is going to be declared the winner of the election. But if nobody has a majority, we're going to eliminate the candidate with the fewest number of votes and rerun the election without them. And we're going to keep repeating that process until someone has won a majority of the votes. So let's take a look at a simple example. In this election, we have 7 votes, which means that a candidate needs 4 votes, a majority of the 7, in order to win the election. The candidates here are Alice, Bob, and Charlie, and so we'll look at the ballots one at a time. For this first ballot, Alice is this voter's top preferred candidate, so Alice is going to get this ballot. This next ballot is also going to go to Alice. This ballot has Bob as their top choice, so Bob gets this ballot, as well as the next one. The next ballot goes to Alice, the next ballot goes to Bob, and the final ballot has Charlie as the top preferred candidate. At this point, Alice has 3 votes, Bob has 3 votes, and Charlie has 1 vote. But remember that with 7 votes in this election, a candidate needs 4 votes in order to win. So at this point, we need to hold a runoff. Charlie has the fewest number of votes in this election so far, so Charlie is going to be eliminated from the race. What happens to the voter who originally voted for Charlie? Well, that voter had a second preference, and their second preference was Alice. So Alice at this point is going to get this last ballot. Alice now has 4 votes compared to Bob's 3 votes, and 4 is a majority, so Alice is going to be declared the winner of this election. That, in short, is how a runoff election works, but it could be a little more complicated. So let's take a look at a more sophisticated example, this time with 10 ballots and 4 different candidates, Alice, Bob, Charlie, and Dave. The first step happens, and we give each candidate all of the voters who chose that candidate as their first preference. And at this point, Alice has 3 votes, Bob has 4 votes, Charlie has 1 vote, and Dave has 2 votes. In a plurality election, or a first-past-the-post election, Bob would win this election now, because Bob has more votes than anyone else. But with 10 ballots in the election, in a runoff election, a candidate needs a majority, or 6 out of the 10 votes, in order to be declared the winner. Since nobody has 6 votes yet, we need to hold a runoff. Charlie, again, is in last place in this election, so we're going to eliminate Charlie from the election, and their voter is going to now vote for Alice, the second preference. Alice now has 4 votes, Bob has 4 votes, and Dave has 2 votes. Still, nobody has a majority of 6 votes, so we need to hold yet another runoff. Dave has the fewest number of votes in this election at this point, so Dave is going to be eliminated. What happens to the people who voted for Dave? Well, the first person who voted for Dave chose Alice as their next preference, and the second voter who voted for Dave chose Charlie as their second preference. But Charlie has already been eliminated, so the vote can't go to Charlie either, so we now look to that voter's third preference, which in this case is also Alice. This means that Alice gets each of the 2 remaining votes, and Alice now has 6 votes compared to Bob's 4. Alice has a majority of the votes in the election, so Alice is declared the winner of this election. Your task in Runoff is going to be to write a program that simulates this style of runoff election. So how are you going to do that? Well, one thing to think about is how you're going to represent this data. And one piece of data you're going to need to represent are all of the candidates and the information associated with them. In this case, in addition to storing the candidate's name and the number of votes they currently have, you'll also want to store a Boolean flag, true or false, representing whether that candidate has been eliminated from the race yet or not. At first, all of these values will be false, because nobody will have been eliminated, but as candidates are eliminated in this runoff process, you might switch those values from false to true. You can represent each of these candidates using a struct that we'll give you, where this struct representing a candidate has 3 fields, a string field called name, an int field called votes, and a bool field called eliminated, representing whether or not that candidate has been eliminated from the election or not.
I don't
We
know.
can store a sequence of
I want to see exactly what they want us to do, because it's like
these
a lot of
candidates inside
arrays.
an array of candidates, where each individual element
This is
in that
basically
array
just video format of all of this garbage, I guess. Well, not even just that, because there's like... I want to finish this video and
one
then
of these
I'll go through
candidate
it.
structs. But the candidates aren't the only piece of information that we need to keep track of in order to run the runoff election. We also need to keep track of information about the voters, in particular about who their preferences are. And to do that, we're going to represent preferences using a 2-dimensional array called preferences.
I love
How do
two-dimensional
you interpret
arrays.
this 2-dimensional array? Well, preferences ij, meaning row I and column j, is going to be a cell.
This is CS50, Harvard's free online computer science class introductory course.
that stores the index of the candidate who is voter i's preference number j. So what does that actually mean? Let's take a look at an example. In this case, we have 3 candidates, Alice, Bob, and Charlie, where Alice is stored at index 0 in the candidates array, Bob is stored at index 1, and Charlie is stored at index 2. What happens if we say something like preferences 0, 0 equals 2? Well, that means we're going to fill into row 0 and column 0 of this array the number 2. And the way to interpret that is that row 0 is talking about the first voter, and column 0 is talking about the first preference for that voter. And the 2 means candidate at index 2, which in this case is Charlie. So preferences 0, 0 equals true means the first voter's top preferred candidate is in fact Charlie.
Oh.
What if we then said preferences 0, 1 equals 0? Well, that would mean we would fill in the number 0 into this slot in the two-dimensional array. We're still on preferences 0, this first row, talking about the first voter. But now we're on column 1, which is here going to represent the voter's second preference. Their second preference is 0, and candidate 0 is Alice. So preferences 0, 1 equals 0 means the first voter's second preferred candidate is Alice. And we can fill in this entire preferences two-dimensional array to keep track of every single voter and every single preference that that voter has. So what do you actually need to do to implement the runoff program? Well, inside of runoff.c, you're going to implement 6 functions that will perform the algorithm of implementing this runoff election. First, you'll implement vote, then tabulate, then print winner,
What is a tabulate?
then
I'm sure he'll go
isTie,
over it.
and then finally eliminate. And we'll go through each of these functions one by one.
Thank you.
Let's start with the vote function. The vote function takes 3 arguments: an integer called voter, representing which number voter is currently voting. It also takes an integer called rank, representing which rank the voter is currently trying to indicate a preference for. Rank 0 meaning their top preference, rank 1 meaning their next preference, so on and so forth. And finally, the function takes in a string called name, indicating which candidate they're currently trying to vote for. So, what is vote going to do? Well, your vote function should look for a candidate called name. If you find that candidate, you should update the two-dimensional array of preferences so that they are that voter's rank preference. And then you should return true to indicate that you were successfully able to record this preference. But if no candidate was found, you shouldn't update any preferences at all, and your function should just return false. Let's take a look at an example. Here again, we have Alice, Bob, and Charlie. And here again, we have a two-dimensional array of preferences, which is going to be stored as a global variable in your program. Let's imagine that this ballot comes along, where the first preference is Alice, then comes Charlie, then comes Bob. Well, Alice is the candidate at index 0 in the candidates array, which means we're going to fill in 0 into row 0 and column 0 of this array, representing the first voter's top preference. This voter's next preference is Charlie, who's at index 2 in the array, so 2 gets filled into the next spot in this preferences row. And finally, Bob is the third preference. Bob, again, is at index 1 in the array, so 1 gets filled in next. And we're going to do this for each of the votes that comes our way. If the next voter
That's
votes for
awesome.
Charlie as their top preference, and Charlie is at index 2 in the candidates array, then we're going to fill in 2 as the first preference for this voter. Bob is the second preference,
this is
index
easy.
1, and Alice is the third
This isn't
preference,
bad.
who is the candidate at index 0.
So you just have a
And we're going to
two-dimensional
do the same
array.
thing for each remaining voter who votes in the
and
election,
fill
until
it
by
up
the
with
end of
all
it,
the
we filled in
values,
the
and then
entire
you're just
preferences
going to-
array for each of the voters and for each of their preferences.
I'm just confused about
Next
the
up is
elimination
the tabulate
thing.
function. And
Actually,
the
that's
job
not
of the
that bad.
tabulate function
It just
is
seems
going
like
to be
there's a
to
lot of
update
things
the
you have to
vote
keep
counts
track
for
of
each of the
here,
candidates
which
to
is just
represent
I'm thinking
how many
about how
votes
you
they
can
currently have.
keep track of them all in an efficient way without needing to make a bunch of extra variables or extra arrays to keep track of this shit. But I don't think it's gonna be that bad.
Well, recall that every voter is
The
going
other
to
one looks
ideally
really
vote for their
difficult.
highest
It's like-
preference candidate.
Oh
But a
my
voter
God.
can't vote for a
I'll do this one
candidate who
first
has
and
already
see
been
if I'm
eliminated.
feeling up to doing the
So
next
each
one.
voter is going to vote for their highest preferred candidate who has not yet been eliminated from the race. So what might this tabulate function actually do?
Okay,
on
I
some
was
sample
not paying
data?
attention to that.
Vote counts. Next
Tabulate.
up is the tabulate function. And the job of the tabulate function is going to be to update the vote counts for
Wait, does
each
that
of the
return
candidates.
something? No, it doesn't return
The tabulate function. And the job of the tabulate function is going to be to update the vote counts for each of the candidates to represent how many votes they currently have. How are you going to do that? Well,
Okay. So you're just going to, let's see, update the vote counts for all the non-eliminated candidates.
recall that
So what you're gonna do is I'm speaking this as if I'm telling you guys what to do. I'm kind of just rubber ducking for myself. First, you gotta loop through all of the candidates. Check if their eliminated value is false. So if they're not eliminated, then it's going to update the vote counts. And to update the vote counts, you're going to use the probably each voter votes for their highest preference candidate. Oh god, this is going to be like, how am I going to avoid nesting this 20 things deep? Oh wait, no. Okay, hold on. You don't need to. I just need to... Okay, now I got this.
every voter is going to ideally vote for their highest preference candidate. But a voter can't vote for a candidate who has already been eliminated. So each voter is going to vote for their highest preferred candidate who has not yet been eliminated from the race.
So the highest preferred candidate. So you're going to loop through them all. But if that first choice isn't eliminated, then you're going to do that. You're going to just I+1 or something.
So
to
what
get
might
to
this
the next
tabulate
one.
function actually do on some sample data? Well, let's take a look at these preferences and these candidates.
I think I have an idea.
None of the candidates have been eliminated yet. Alice's eliminated status is set to false, and so is Bob's, and so is Charlie's. Which means that since nobody has been eliminated, every voter gets to vote for their top preferred candidate. This first voter, for example, is voting for candidate 0, who's Alice. So our tabulate function would update Alice's vote total, changing it from 0 to 1. Next up, this voter is voting for Charlie, the next voter is voting for Bob, the next voter is voting for Charlie again, and the final voter is voting for Alice. So at the end of our tabulate function, we should have recorded in our candidates array that Alice has 2 votes, Bob has 1 vote, and Charlie has 2 votes. But what happens?
Oh, okay, cool. So the way that I'm gonna avoid nesting it is just inversion again. I love inversion. I'll go back for a second. So this, I'm gonna loop through all of the candidates and check if they are not eliminated. So what I'm gonna do with that is just have an inverted, if candidates eliminated, then return. So it'll return out of it, or it'll continue through the loop. It won't return because we don't want it to end the loop. It'll continue through the loop. I'm gonna set up some boilerplate for that right now. While I'm going along this, I'm cooking. This isn't gonna be that bad, really. So first thing we're gonna do is we are going to write the vote function. So if the name is a match for the name of the okay. Do I need do they have okay, the distribution code. Cool. CD clear what's the cool, I remembered. So it's a runoff. Oh shit, I didn't even unzip it. Oops, I'm an idiot. Oh god. Unzip runoff.zip. Shit. Not. Oh god. Okay, rmrf runoff.zip. Here we go. Runoff. Clear. There we go. Runoff.c. Okay, this is about to be the most complicated program yet that I've tackled. Let's zoom out a little bit just to see what we're working with. All right, cool. So vote. We're just gonna do step by step. This isn't gonna be difficult. They do a lot of the heavy lifting first. Holy shit! Why do they nest so deep? Please don't tell me my code's gonna look like that. Oh my god, how many is that? 1, 2, 3, 4, 5. Why? That looks like buy food to feed your cat, dude. And I'm assuming same with the other one. I can't touch this code that they have here. The only thing I'm supposed to do is finish these functions, which is actually pretty good practice. Yeah, let's tackle this. This isn't gonna be that bad, and we'll figure it out. Alright, let's just see what it's doing here. Check the arguments, candidate count, populate the array just like the other one. Gonna loop through them all, set their default values. Like, the thing is, I don't like the fact that they don't let me touch all this. Like, I would much rather write this all from scratch again. Because this is something like I'd break into a function. I'd break this down into a function that's like set assign candidates or some shit, something like that. Or yeah, like I'd make that into a function just to have it align, like one line, and then vote count. Like you could make that into a function. And this too, I get this is like for your 2D array, but you don't need a whole nother like I don't know. I guess that's just C syntax. Really, like, you wouldn't nest deeper than that. But that's just kind of how they... I don't know. That's a lot of... That's like... It's like 5 nests deep, which I just don't like. Ever since I became a never nester, I hate looking at deeply nested code. It's awful. Fortunately, though, they're not terrible with it. It's just a lot of if statements and stuff. Like, it's easy to keep track of what's happening. It's just... I don't know. It still doesn't look great because they're just nesting so far deep. But whatever. At least it's readable. Alright. So what we're going to do is if their name is a match for the name of the valid candidate, we should update the global preferences array to indicate that the voter has that candidate as their rank preference. Keep in mind 0 is the first preference, 1 is the second, etc. You may also assume that no two candidates have the same name. So, if name is a match for... We'll start there. So it's like global preferences array. Okay. Cool. So I is the voter, J is their candidate. So what we're gonna do is vote for the... Or we're going to update the vote, so... Wait. Update the global preferences array to indicate that the voter has that candidate as their rank. Wait, what? Am I stupid? Okay. If the preference is successfully recorded, the function should return true. I am so, like, brain fried right now. I don't know what I'm looking at. So, what is it asking me to do? If the name... So, if the candidate name is a... Oh, right, because this is the command line. Or no, this is the voter input. This is what the voter is putting in as their candidate. Oh, okay, right. I'm like, thinking... I'm thinking so ahead. I'm so stupid. So, this is only... What this function is doing, this is actually... updating their list of candidate picks based on the string input that it takes. So what this is doing is we just need to assign, and it already gives me the rank. We're just going to say, first of all, I'm going to invert this. So we're going to return true. So if stir compare name candidates I, or candidate's rank, rather, dot name equals 0. Then we're just going to return false. But then we're going to go into the voter. So preferences is the voter and then the candidate. So it's just voter and then rank. So preferences, voter, rank equals candidates rank name. Right? Am I doing that right? Well, no, you can't set a string equal to another string. Well, call it candidate count. Let me see what this function's actually doing when you input the vote. So the vote, okay. The voter count, and then okay, yeah. So this is just J is just the second, like the first rank, the third rank, the first rank, the second rank, the third rank. And then the first one is actually the which voter is currently in the loop. So candidates so which one's candidate count? J. Okay, yeah, good. So we're doing the right one. Preferences. Yeah, that one works. That's good. That's all it's doing. And oh. If candidate name was already So I gotta assume that oh. Wait. It says you may assume. Does that mean they already have it done for me? I'm just gonna assume that's what they mean. I'm gonna assume that it already... Man, they really took a shit up a notch. I'm just gonna assume that's fine. I don't... They just said you may assume that no two candidates will have the same name. So do they want me to write code for that or not? Have they already written that for me? Is that what I was supposed to assume? Eliminate anyone. Tie. Eliminate last. Well, they don't say anything explicitly in here, I guess, at least from reading the comments. But I'm probably going to assume when one of their things is eliminated. Well, no, because you have to... I mean, it wouldn't matter, though, if you think about it. Because with the runoff, say you vote for Alice twice. You have Alice twice on your list. And Alice is eliminated. Then it would just ignore every time you have Alice on your thing. But problem is, it needs to win majority. So it needs to win half of the total votes plus one. So if like multiple voters just put a voter that's gonna get like kicked out anyways at the end, then it ends up being a stalemate and nobody wins because there's literally not enough votes remaining. I'm just gonna go with this for now. I'll come back to it if I have to. Oh wait, if there is one. Okay. So print the winner of the election if there is one. I'm to assume that it might not I don't know. Let me just watch the video.
Voter is going to ideally vote for their highest preference candidate. But a voter can't
Well, actually,
vote for a candidate.
let me start working on that first. For int I equals 0, I is less than candidate. So there's a variable for it. Candidate count. Candidate count. I plus plus. Oh, plus. No way. No way C++ is called C++. Because it's C incremented. Oh my god, no way. That's... I called it. They just called it C++ because it's just C but incremented by 1. This is C. This isn't C++, but that's crazy. C with classes. That's funny. It's like the next... That's awesome. That's so fucking nerdy. Why is it called C sharp though? Oh, literally inspired by the musical notation. Where a sharp symbol indicates that the written note should be made a semitone higher in pitch. Yeah, so it's basically C++, but musically instead. I don't know. That's so nerdy. That's cool. I never knew that. A little bit of learning. If candidates I dot eliminated equals false, we're just gonna return or no, we're just gonna continue.
who's already been eliminated. So each voter is going to vote for their highest preferred candidate who has not yet been eliminated from the race. So what might this tabulate function actually do on some sample data? Well, let's take a look at these preferences and these candidates. None of the candidates have been eliminated yet. Alice's eliminated status is set to false, and so is Bob's, and so is Charlie's. Which means that since nobody has been eliminated, every voter gets to vote for their top preferred candidate. This first voter, for example, is voting for candidate 0, who's Alice. So our tabulate function would update Alice's vote total, changing it from 0 to 1. Next up, this voter is voting for Charlie, the next voter is voting for Bob, the next voter is voting for Charlie again, and the final voter is voting for Alice. So at the end of our tabulate function, we should have recorded in our candidates array that Alice has 2 votes, Bob has 1 vote, and Charlie has 2 votes. But what happens in a more complex scenario, where, for example, Bob may have been already eliminated from this election, and we want to tabulate these votes again? Well, we'd go through the array, much as we did before, and see that the first voter was voting for Alice, and the second voter is voting for Charlie, the candidate at index 2, and the third voter is trying to vote for the candidate at index 1, who in this case is Bob. But Bob's already been eliminated, so the vote can't actually go to Bob. So instead, this voter is going to look at their next preference, candidate number 2, who in this case is Charlie. Charlie's still in the race, and so Charlie gets this vote, and his vote total gets updated from 1 to 2. The next voter votes for Charlie, no problem, and the final voter votes for Alice. So by the end of it, Alice has 2 votes, and Charlie has 3. So that's what your tabulate function is going to do. Go through each of the voters and update the vote counts, making sure to only update vote counts for candidates who are still in the race. The next function you're going to write is print winner. The print winner function is going to be a function that's ultimately going to be tasked with printing out who the winner of the election is,
So,
if there is a winner yet.
in theory, what I can do is shit. What the fuck? Where's my arrow key? There it is. So do... Fuck. I don't know. I gotta take a break. I think I'm gonna just end the stream here. I don't know. I think I'm done streaming for now. My brain's a little bit too fried. This is a